Welcome to the rigid body equations of motion. Today we are going to discuss the torque-free motion of a rigid body. In the absence of net forces or torques, the center of mass is either at rest or moving uniformly. Thus, it can be dropped from the problem as the dynamics only involves motion about a fixed point. Euler's equations then acquire the form here, which follows simply from the fact that the external torques vanish. And two first integrals of motion for these equations are given by the kinetic energy and the total angular momentum vector. This provides solutions to Euler's equations in terms of elliptic functions, but the results themselves are not very illuminating. However, an elegant geometrical description of the motion follows from what is known as Poinsot's construction. So in the following pages we will discuss mostly the motion from a qualitative perspective, and then most of these results will follow from rigorous calculations. Consider then a frame of reference which is aligned with the principal axis system and which measures the components of rho along the instantaneous axis of rotation. So we are interested in equation 543, which if we put together with the value of the kinetic energy with respect to rotation about this axis, then it means we can recast the vector rho in these two equivalent forms, which include the angular velocity and either the moment of inertia scalar or the kinetic energy. Then we can define a function f of rho as the scalar obtained by contracting the inertia tensor with the vector rho, and its values are given by the sum here in terms of the components of rho and the principal moments of inertia. The surfaces where this function f has a constant value are ellipsoids, and in particular for f equals with 1, these correspond to the inertia ellipsoid. As the direction of the axis of rotation changes in time, rho moves accordingly, its tip tracing a path on the inertia ellipsoid. At that point, the gradient of f with respect to rho furnishes the direction of the corresponding normal to the inertia ellipsoid. And it's very easy to calculate this gradient. It follows just from the definition of f. There are very simple calculations which lead you to this expression and to the final result here. So the gradient is proportional with the angular momentum vector and inversely proportional with the square root of the kinetic energy. So we see that the angular velocity moves in such a way that the corresponding normal to the inertia ellipsoid is aligned with the angular momentum. For torque-free motion, the angular momentum is fixed in space, and thus the inertia ellipsoid fixed to the body must move in space in such a way so as to preserve the relation between the angular velocity and the angular momentum. Furthermore, the distance between the origin of the inertia ellipsoid and the plane tangent to it at the point rho must remain constant in time. So if we do this simple calculation, the dot product here divided by the magnitude of L is equal to this expression, from where it follows that the left-hand side here is given by this quantity. So given that both the kinetic energy and the angular momentum are conserved, the tangent plane is found at a fixed distance from the origin of the ellipsoid. The normal to the plane is aligned with the angular momentum and fixed in space, hence we speak of what is known as the invariable plane. The inertia ellipsoid rolls without slipping on the invariable plane, with the origin of the ellipsoid at a fixed distance above the plane. There is no slipping since the motion is guided by rho, the direction in which the body is momentarily at rest, as this is the direction in which the angular momentum vector points. The curve traced out on the inertia ellipsoid is known as the pull-hode, while the one traced on the invariable plane is known as the hair-pull-hode. In conclusion, the direction of the invariable plane fixes the angular momentum, and the height of the inertia ellipsoid above it fixes the value of the kinetic energy, these quantities being the initial conditions of the problem. Then, through geometry, one determines the pole hold and the hair-pole hold. The direction of the angular velocity in space is that of ρ, while the instantaneous orientation of the rigid body is provided by the orientation of the inertia ellipsoid, which is fixed in the body. For a symmetrical body, the inertia ellipsoid is an ellipsoid of revolution. The pole hold is a circle about the symmetry axis of the ellipsoid, and the hair-pole hold is also a circle. For a body observer, the angular velocity moves on the body cone intersecting with the inertia ellipsoid on the pole hold. A space observer sees the angular velocity on a space cone intersecting the invariable plane on the hair-pole hold. The torque-free motion of a symmetrical rigid body is the rolling of the body cone on the space cone. If the moment of inertia along the symmetry axis is smaller than the other two, the inertia ellipsoid is prolate and the body cone rolls outside the space cone. Otherwise, the inertia ellipsoid is oblate and the body cone rolls inside the space cone. In either case, the angular velocity precesses about the symmetry axis. Now, the Poinsot construction shows how the angular velocity moves, but says nothing about how the angular momentum looks in the body axis. To this end, we need to introduce another structure, which is the Binet Ellipsoid. That follows from equations 525 and 526, as shown here. So it involves the kinetic energy written as a sum of three terms, which are the squared components of the angular momentum divided by twice the corresponding principal moments of inertia. Now, for a general asymmetric body where the moments of inertia can be arranged as shown here, we immediately have this equality. So this holds generally regardless of how their values are ordered specifically, but we are going to assume this throughout the discussion here. So then the semi-major axes are given by these three square roots, and the conservation of the angular momentum will then imply the equality here, which is nothing but the equation of a sphere in a space given by the values of the three Cartesian components of the angular momentum. So the point is that the angular momentum moves in such a way so as to describe a path both on the ellipsoid of equation 545 and on the sphere of equation 546. So it moves on their intersection. Then to find the trajectories, this quality must hold, and you can very easily see that these surfaces intersect if the magnitude of L lies between these two values. And you can just plug them in the equation and work the algebra out to see if it makes sense or not. So in our convention, the convention specified here, the sphere is outside the ellipsoid along the LZ axis and inside along the LX axis. And from 540, it will follow that if all components of the angular velocity are constant, then these three equalities hold. So two components must be zero, and the non-vanishing one is aligned with a principal axis. However, not any such alignment is stable. That is, not any such alignment will not drift far from the principal axis under small perturbations. This occurs about the axis with extreme values for the moments of inertia. Slight deviations will shorten the radius of the angular momentum sphere, and the intersection with the Binet ellipsoid about the axis of largest moment of inertia lead to a small circle about that direction, hence stable motion. So this is something which again we will prove rigorously a bit later, the conditions in which the motion is stable or unstable. When perturbing the motion about the axis with the smallest value of the moment of inertia, the radius of the angular momentum sphere is slightly larger than the axis of the ellipsoid, and the intersection is, as in the previous case, is a small closed figure about the axis leading to stable motion. However, at the intermediate axis, the motion is unstable. The reason being that in this particular case, the radius of curvature of the ellipsoid is greater than that of the contact sphere in one direction and less in the perpendicular direction. This becomes very important for the stability of spinning spacecraft if you are looking for a practical application. For dissipative systems, the motion is stable only about the axis with the largest moment of inertia. This is due to the fact that the kinetic energy about a given axis of rotation has the value here, so for a slight change in the kinetic energy, the angular momentum will have to move such that the spinning axis is about the axis requiring the lowest value of the kinetic energy for a given magnitude of the angular momentum. Now we will look more rigorously at the motion of a torque-free rigid body, and we will begin by considering a symmetrical rigid body having the third component of its angular momentum aligned with the symmetry axis, and we will let the moments of inertia along the perpendicular axes to the symmetry axis to be equal due to the symmetry of the body. Then Euler's equations will have these expressions where due to symmetry it follows immediately that the third component of the angular velocity in the intrinsic frame is constant, and then this allows us to rewrite the first two equations as here in terms of this additional constant capital omega, which is given by the two non-equal values of the principal moments of inertia and the angular velocity about the symmetry axis. And then we can very simply solve these just by taking the time derivative of one of them. Let's say we take the time derivative of the first one and use the second result to obtain the equation of a simple harmonic oscillator. And obviously the same works for the second equation. So the solutions will be of this form, and we conclude that the component of the angular velocity which is perpendicular to the symmetry axis has the form shown here. So so this vector has a constant magnitude and rotates uniformly about the symmetry axis with angular frequency capital omega. It follows then that the angular velocity itself is constant due to the fact that the parallel component to the symmetry axis is also constant, as we have just seen. So the angular velocity itself is conserved, and it precesses about the symmetry axis with the same frequency, the one shown here as predicted by the Poinsot construction. So then we can define the vector capital omega by this expression, and then through equation 5.47 we can find the time derivative of omega in the intrinsic frame as given by the cross product here. So the angular velocity precesses with frequency omega in relation to the body set of axes, which themselves rotate in space with the frequency given by the vector omega. And the closer I1 is to I3, so the closer the body is to being spherical, then the smaller capital omega will be relative to the magnitude of the angular velocity. And then obviously we can, in terms of the components of the angular velocity and the principal moments of inertia, we can immediately write the kinetic energy and the magnitude of the squared magnitude of the angular momentum vector, and solving these equations for the kinetic energy and for the magnitude of the angular momentum, we can obtain the amplitude A, which appeared in the solutions for the first two components of the angular velocity and the parallel component to the symmetry axis. Now, we know that in the intrinsic frame the angular momentum so it's generally given by this contraction, but in particular in the intrinsic frame, or in the body set of axes, then we will have the simple expression here. And we also know that since the motion is torque free and the angular momentum vector is conserved, its direction as seen in the laboratory system is fixed in space, and we can choose it to be, let's say, aligned with the vertical in the laboratory frame. And then we can express the versor corresponding to the laboratory vertical. We can express it through the Euler angles in terms of the body set of axes. So it's the expansion here, and then just by comparing the two, it follows immediately that the Euler angle theta is constant and is given by this value. And then furthermore, if we use this result together with the squared magnitude of the angular momentum and the fact that the squared amplitude is given by the sum of squares of these components of the angular velocity, and since we know how to write these in the body frame, if we put all of these things together, we can find the precession rate about the laboratory vertical. So the time derivative of the Euler angle phi is simply given by this quantity, and then the angle itself just increases linearly in time. And of course, from the value of omega 3 as given in terms of Euler angles in the body set of axes, we can obtain the precession rate for the spin of the rigid body about its symmetry axis, and we just obtain as follows. Naturally, we just obtain minus omega, so the angle itself again moves linearly in time with the constant omega. So the sign changes due to the fact that we're shifting from the we're shifting from what is viewed as a passive rotation in the body frame to an active one, as is seen in the laboratory frame. And in any case, with these values, then we can easily write the angular velocity of the rigid body in the laboratory frame as shown here. Now with this result, we can show another very important point, namely, first of all, we can show that as viewed in the laboratory frame, the angular momentum vector, the angular velocity vector, and the symmetry axis of the rigid body are all in the same plane, and it follows from the fact that this dot product is 0. And then we can put several more things together, namely, if we just write out the cross product between the angular momentum and the angular velocity in terms of the angle theta prime between them, and we also use the fact that from our kinematical law 4.86, this cross product is in fact equal with the contraction of the inertia tensor with the time derivative of omega. Then putting all of these things together, we can very easily obtain the result here. So this is the relation between the theta prime angle is the angle between the angular momentum and the angular velocity, and theta second is the angle between the angular velocity and the figure axis of the rigid body. So the two are proportional, the proportionality constant being the precession rate capital omega divided by the precession rate of phi of the Euler angle phi. And the reason why this is important is because it leads to the proof of another conclusion that followed from the discussion of the Poinsot construction. Namely, we can think of the coordinates of an arbitrary point of radius r as being found on the intersection of two cones. One cone having as symmetry axis the laboratory vertical direction, and the other having as a symmetry axis the figure axis of the rigid body. So the row and row second are simply the cylindrical radii for the cones in these two systems, and obviously they have the expressions here. So if we put them together, we can obtain we can find the coordinates of the point along either axis, be it the laboratory vertical or the figure axis of the rigid body in terms of this expression. And the reason why this is useful is because if we would like this point to precess about these two directions with the same velocity. So in other words, if we would like these cones to roll upon one another, then we find that the unknown precession rate, which corresponds to the precession about the cone centered on the figure axis of the rigid body, then this precession rate is given by the value here, and it turns out that it is exactly equal with capital omega. So it's the precession rate that we have shown earlier to be valid for the intrinsic motion of the angular velocity of the rigid body. And then from the fact that rho is proportional to the angular velocity, it follows immediately that both the pole hold and the hairpin hold are circles, and this leads to the above stated conclusion. So everything closes up consistently. With regard to asymmetrical rigid bodies undergoing torque-free motion, while it is no longer possible to solve the Euler equations in terms of elementary functions, we can still use the constants of motion to eliminate two of the angular velocities and then integrate for two components of the angular velocities and then integrate for the remaining one. So I've written Euler's equations compactly here, and the values of the corresponding energy I've denoted it by E, but it's just the kinetic energy and the square of the angular momentum. And if you put these together, the general quadrature that you will reach should be something like this. I've done the calculation only once. Dimensionally, it seems to be correct, but if you're interested, you should check very carefully to see that this is indeed the case. So regardless of which two components you eliminate, you should get to an elliptic integral of this sort, which is written in terms of the principal moments of inertia and the constants alpha, beta, and gamma, which have their expressions given here in terms of the energy, of the magnitude of the angular momentum, the principal moments of inertia, and this additional quantity, and these additional quantities, I should say, the small l's, which are given by such expressions. So formally you have a solution of this sort, but obviously, at least for very general discussions as the one here, it's not something that is very useful. It makes more sense if you have a very specific practical application where you absolutely need an exact solution of one form or another. Furthermore, assuming once again the case of an asymmetrical rigid body with the principal moments of inertia ordered like here, we can now study the problem of stability that was mentioned earlier. Namely, we will consider that we have a dominant component of the angular velocity about some axis, let's say about the first one, and then the other two components are very small in the sense that their products will vanish. And in that case, the Euler equations will reduce to the form shown here. So we have a constant value for the dominant component, while the other two components will obey the equations for a simple harmonic oscillators with the squared frequencies shown here. And then just for cyclic permutations, we can obtain the corresponding squared frequencies for the other two cases. So if we're taking the dominant component to be the second one and the first and third one are small and so on. And what you see is that in the first case, so for the smallest principal moment of inertia, these squared frequencies are positive numbers. So we are describing just simple harmonic motion. So let's say the rotation is stable. If we look at the third component, once again we see that this square is a positive number. So once again we are discussing stable motion. But in the second case, we see that this is in fact a negative number because of the way the values of the moments of inertia are specified. So this being negative, and then it means that the complex exponential describing harmonic motion in fact becomes a real exponent. So the motion is unbounded, and in other words, it is unstable about the intermediate axis. One further application of this discussion regards the motion of the planet itself. So we are working now in the approximation where the external torques acting on the Earth from objects in the solar system are small enough that we may approximate its rotation as being that of a free body. Now for the planet, the I1 is smaller than I3 due to the fact that Earth is flattened at its poles, and the quantity that we have previously discussed in relation to the frequency capital omega is known in the specific case of the Earth. It is referred to as being the dynamical ellipticity. So it's the ratio here, and for Earth it has this specific value. And then we can calculate capital omega according to its definition that we have derived earlier, to be given by the value here, which is approximately this ratio. And we keep in mind that the third component of omega is practically equal with the magnitude of the vector. So it's just the angular velocity of the Earth as it rotates about its axis. So what this calculation suggests is that we would expect a precession period of 306 days, or roughly 10 months, and this would be visible as a change in the apparent latitude of points on Earth's surface. And such a motion is indeed observed, and its amplitude is of roughly 10 meters. In that case, so if the amplitude is of roughly 10 meters, its average value is about half. So we can say that during this motion, the distance between the figure axis of the planet and the axis of rotation is then just the radius of the Earth times the angle between them. So this has to be approximately 5 meters, and and then what follows, so immediately we can find the value of this angle to be the one given here, and we have shown that this relation holds between the angles corresponding to the separation of the angular momentum and the angular velocity, and respectively the angular velocity and the figure axis. And this ratio is given by approximately by the value here. So the conclusion is that what we want to show is that the distance on the Earth's surface between the angular momentum vector and the angular velocity vector is at most of about 1.6 centimeters. Now, what happens in reality is that the period is significantly different from the one predicted by these considerations, and it was discovered by Chandler back in 1891, as having the value of about 432 days. And the dynamics is quite a bit more complex, and it carries the name of the Chandler wobble. The difference between it and the rigid body precession comes from the planet's elastic deformation, with accompanying responses of the oceans at core. What happens is that the part of the Earth follows along with the shift in the rotation axis, reducing the difference between the principal moments of inertia and increasing the period. If it were to be the case of a perfectly fluid Earth, then it would simply readjust instantly, and there would be no observable precession. This wobble has a characteristic damping time of roughly 30 years, so it is continuously maintained by some sort of random excitation. Possible causes that have been investigated over time have included coupling to irregular core motions, atmospheric motions, and earthquakes. However, the present belief is that the wobble is maintained by interactions between the atmosphere and oceans, which leads to ocean floor pressure variations. Apart from the Chandler wobble, there is also a smaller 12-month variation driven by seasonal mass redistribution throughout the Earth. Thus, the latitudes of observatories vary with a beat of the 14 and 12-month processes, resulting in a cycle that has about 6 years. In summary, we have discussed the torque-free motion of a rigid body in terms of the Poinsot construction involving the inertia and Binet ellipsoids. We solved the Euler equations for a torque-free symmetrical rigid body, and we have discussed the free body precession. We explored general features of torque-free motion for an asymmetrical rigid body, including the question of stability for its motion. The free precession of the Earth was investigated, leading to a discussion of the Chandler wobble. In the following, we will solve simple problems involving rigid bodies that are moving under various constraints in a uniform gravitational field, and we will be doing this as a preparation for the more advanced discussion of the heavy symmetrical top. So, with that being said, I want to thank you very much for watching. I hope you found this discussion worth your time, and I will catch you later. Goodbye.